Welcome to our introduction on machine learning for predictive maintenance. We will focus in this recipe on building a classification model for a labeled dataset available on Kaggle with the purpose to classify different failure types. This recipe will enable you to build classification models for multi-output challenges. Using AI in businesses can help to become more efficient and competitive. With the rise in digital technology, this can happen. System failure occurs often across all machine and equipment applications. One way in which artificial intelligence is used is in the combination of machine learning and maintenance. Maintenance is defined by the norm EN 13306-168 as the combination of all technical, administrative and managerial actions during the life cycle of an item intended to retain it in, or restore it to, a state in which it can perform the required function. Three forms of machine maintenance to keep equipment running well are: first, run to failure, alternatively referred to as corrective maintenance, is when maintenance is performed only after a machine fails. Second, preventive maintenance, also known as time-based maintenance and planned maintenance, is when maintenance is performed on a regular basis according to a schedule. And finally, third, predictive maintenance is a maintenance strategy that improves efficiency by allowing a prediction of the remaining usable life of the machinery, also known as proactive maintenance. With developments in sensing and Internet of Things technology, the importance of predictive maintenance has grown in recent decades. The key benefit of predictive maintenance is that it reduces unexpected downtime and associated expenses while also extending the equipment's lifespan. Predictive maintenance may be made easier using a variety of ways. Using historical data and analyzing it with machine learning algorithms is one possible way. Because of the increased availability of processing power for sensors and failure data acquired in recent years, machine learning approaches are now quicker than traditional statistical survival analysis. Here are some examples for predictive maintenance implementations and monitoring. Different strategies for predictive maintenance can be supported by the application of machine learning. Among them are regression models for predicting the remaining usable life, as well as classification models for predicting failure within a certain time range. Problems that need predictions based on continuous input and output can be solved using regression. To categorize and anticipate the likelihood of problems, machine learning uses classification. Because certain things about machinery can be tracked, predictive maintenance is based on the idea that you can figure out how long the equipment will last. Hence, this type of maintenance strategy entails various significant advances in the manufacturing and maintenance processes, which have the potential to significantly lower production costs. First, because it is not reliant on periodic maintenance periods that are restricted to average lifetime, predictive maintenance can minimize the number of needless maintenance actions. As a result, the total number of maintenance actions performed during the life of a machine may be reduced. Second, not only can excessively early maintenance activities be avoided, but so can excessively late maintenance activities, as equipment may fail before the next periodic maintenance interval is reached, because the intervals are based on average lifetime, which is likely to include significant positive as well as negative deviations from the average. Because of the unique structure in which a given component is used in bigger machinery, for example, both the reduction of needless maintenance and the decrease of failures result in higher productivity and less downtime in the manufacturing process. Predictive maintenance is the most cost-optimal maintenance type given its potential to achieve in overall equipment effectiveness. How can data be gathered within condition monitoring? First and foremost, inspection-based monitoring is the strategy that receives the least attention when it comes to monitoring a machine's status and collecting important data. With inspection-based monitoring, data is gathered at regular intervals. The intervals are changed in accordance with observed and collected data on the present and projected conditional state of a machine or component. When a machine or component is in its present and expected conditional state, the intervals are adjusted in accordance with the observations and data acquired about the machine or component. Second, since advances in sensor technology have made sensors for many sorts of metrics more affordable, the bulk of studies have focused on sensor-based monitoring. Various kinds of sensors, such as those that detect vibration, temperature and acoustic emission, are utilized to gather the necessary information in sensor-based monitoring systems. It is important to note that sensor-based monitoring and inspection-based monitoring are not mutually exclusive, since sensor equipment is often required in order to complete the inspection. Generally speaking, the use of sensor technology is more suited for an integrated predictive maintenance system, since it is critical for effective continuous monitoring and is more affordable. A machine or component's remaining usable life may be estimated with the use of continuous monitoring, which collects important monitoring data throughout time. When compared to inspection-based monitoring, the quantity of data obtained is much more, since inspection-based monitoring is only a periodic snapshot of the conditional state of a machine. Although condition monitoring can be used to predict failures, condition monitoring alone cannot be considered predictive because it only allows for the identification of parameter changes that occur before a failure. It does not allow for the prediction of a relatively narrow future period of time during which the parameter changes occur and thus the failure may occur. The inability to schedule maintenance activities in a timely manner prevents people responsible from doing efficient maintenance tasks, such as determining the most cost-effective time frame for shutting down the manufacturing process for maintenance activities. So, a good prognostic method is needed to turn the data that was collected into useful information for predicting when things will go wrong. On the other hand, corrective maintenance is always done after there is a problem. Following that, the machine can either be repaired immediately or at a later time. This strategy, on the other hand, may result in a significant reduction in manufacturing time as well as costly maintenance. Reactive maintenance and corrective maintenance are two terms for the same thing. Preventive maintenance, also known as proactive maintenance, aims to keep things running smoothly. As a result, preventive maintenance policies are classified into two groups. First, preventive maintenance, which involves performing maintenance tasks at predetermined intervals based on historical average equipment life. On the other hand, condition-based maintenance continuously examines a machine's present state and plans maintenance tasks accordingly. It is possible to use three different types of condition monitoring methods in this situation: request-based monitoring, scheduled monitoring, and continuous monitoring. Condition-based maintenance, on the other hand, keeps an eye on a machine's current state and plans maintenance actions around it. Monitoring on demand, planned monitoring, and continuous monitoring are all viable options here. The first two methods are primarily inspection-based, whereas continuous monitoring is usually accomplished through the use of sensors. The first benefit of predictive maintenance is that it could decrease the number of spare parts that need to be kept in stock. A reliable predictive maintenance system would make it possible to only keep the spare parts that will be needed soon instead of keeping every spare part that could be needed. With less spare parts in store and a smaller overall storage space, the predictive maintenance system can keep the maintenance process running smoothly and prevent production downtime caused by a lack of readily available replacement parts. Secondly, some believe that predictive maintenance might actually help to extend the total life of machines and its components. Because predictive maintenance monitors a machine's health and anticipates its remaining usable life, it decreases the danger of a fatal breakdown, which might shorten the machine's lifespan even with thorough corrective maintenance. As a result, because predictive maintenance systems can help to avoid needless maintenance activities, they are also beneficial in that they can help to extend the life of machines. This is because every maintenance activity puts the machine at risk because a maintenance action and replaced components represent an intervention in the machine's structural design. Fourth, Because predictive maintenance systems are capable of detecting faults in the future based on monitoring data and prognostic methodologies, the frequency of fatal breakdowns can be cut in half. There is always the possibility that a machine or component will fail prior to the next scheduled maintenance interval, even when using a conventional scheduled maintenance policy based on historical data about the lifespan of a machine or component. After all, the maintenance interval is only an average that includes outliers. A predictive maintenance strategy, on the other hand, monitors the machine and its components on a frequent or even continuous basis and prompts maintenance activities regardless of whether or not the machine or component is in use. As an alternative, a predictive maintenance strategy periodically or even continuously checks for malfunctions in the machine itself and its components and takes action regardless of how long the equipment or component has been in use. Cost-sensitive learning. When it comes to predictive maintenance systems, training is the process of identifying the model parameters that best describe or explain the observed device behavior. A cost function, which compares actual and expected conditions for all devices to measure model performance, is commonly used to determine best fit. When training a machine learning model, cost-sensitive learning takes into consideration the costs of prediction mistakes as well as possibly other expenses. It is common to think of the predictive maintenance task as a binary classification problem because a device can be either broken or fully operational in a certain amount of time. The accuracy, recall, and F1 score are standard cost functions for binary classification that are based on the confusion matrix. However, the most significant drawback of these confusion matrix-based performance indicators is their lack of understanding of the cost and impact of the predictive maintenance strategy on the organization. Important factors for a viable predictive maintenance strategy depend on the business case and include possible expenses for ticket diagnosis and triage, field trip and repair, components and shipment, as well as unavailability. We treat predictive maintenance as a binary classification issue, since a machine may be classified as functioning or inoperative during a certain forecast period. When we think of predictive maintenance as a binary classification issue, it's because a machine may be classified as either functional or inoperative depending on how often it is predicted to work. The accuracy, the recall, and their harmonic mean, the F1 score, are some of the most often utilized measurements. In many predictive maintenance applications there is a mismatch between maximizing F1 score and minimizing maintenance cost. It is not always desirable to misclassify an example from the majority class as an example from the minority class known as a false positive, but it is less critical than misclassifying an example from the minority class as belonging to the majority class known as a false negative, which is more serious. Certain costs due to part degradation and failure occurs during machine lifecycle. Thus it is evident to differentiate between the traditional reactive form of maintenance and predictive maintenance. Cost drivers for maintenance activities are: first, incident documentation and maintenance scope planning. Second, repair time and part replacement. Third, downtime of faulty machine. Having a look in the confusion matrix, for reactive maintenance activities sum of true positives and false negatives are relevant. For predictive maintenance activities sum of false positives and false negatives in case healthy machines are falsely classified as faulty, which results in additional costs through repair time and part replacement. So here a brief summary what items have been explained. Main purpose of this introduction was to get a basic understanding needed for future projects, which will be focused on applying machine learning algorithms on predictive maintenance problems. I hope you have been able to get an accurate and basic understanding in terms of benefits and differentiation of predictive maintenance, cost-sensitive machine learning approach. We will shed light on tailoring cost-sensitive learning for our predictive maintenance project and get an understanding what cost impacts quantity of false negatives and false positives will have. In our upcoming recipe we will use boosting algorithms with multi-class and multi-output algorithms. Now we are ready and carry on our journey and apply our skills for building machine learning models for predictive maintenance. Our recipe is based on a dataset which is available on Kaggle. The dataset consists of 10,000 data points stored as rows with 14 features in columns. Further details of the dataset will be shed light on later. Let us get started within Google Colab to create our machine learning model for a predictive maintenance problem in order to classify failure types. First, as in all machine learning applications, let us create our necessary environment by downloading basic libraries in order to kick off creating our classification model. We install scikit-plot and imbalanced learn. Imbalanced learn library is required for creating of synthetic data. Then, we import NumPy, pandas, and for data visualization Matplotlib and Seaborn. From Sklearn we import all necessary machine learning algorithms and metrics for model evaluation. The CSV files, which includes the necessary datasets, will be uploaded to the Google Colab, and finally a dataframe is created for further usage. Now we can display our dataframe DF and we can see the features like air temperature, process temperature, rotational speed, torque and tool wear. Additionally, we cross-check the amount of data and distribution of the target label, failure type, and can conclude that we have a highly imbalanced dataset for training our model. Here let us see what a heat map can indicate and if correlations exists among feature and class columns. Now we would like to understand which column values do have a significant correlation and therefore need to be considered. Correlation is between -1 and 1. In case correlation is near plus and -1 and significantly above plus and -0.1, we can assume high correlation between two parameters. Let us check how many nulls are in our dataset. Many machine learning estimators demand that datasets be standardized. However, if the characteristics are not normal distributed, they may behave non-normally except for tree-based models. In order to effectively implement any of the data transformation strategies, it is recommended at least to visually analyze each feature first. Simple histograms and box plots can almost help to detect distributions. For our dataset, we create a histogram for all features in order to understand the distributions. Now let us visualize distribution of features to get a better understanding and preparation. How to pre-process our data before applying machine learning classification algorithms. Now, let us visualize parameters dependent on themselves to have a visual insight of distributions. We need to visually understand how different failure types in the minority class are distributed. Finally, we create synthetic data samples out of the labeled minority class. A very common and widely used approach synthesizing new data examples is called synthetic minority oversampling technique, or SMOT, which creates artificial samples of the minority class through interpolation. We also like to make reference here to another video which is linked for you to get a better understanding about SMOT. Please follow link in video. We will use one variant of SMOT called SMOT-TOMEC to create system samples of minority class failure type like power failure, tool wear failure, overstrain failure, random failures and heat dissipation failure. We then create a new provisional data frame to understand the distribution of minority class failure types compared to the majority class failure types. We plot finally as an example the rational speed depended to tool wear to understand the new created synthetic data. Finally, we have an equal distribution of failure types, and it is highly recommended to cross-validate the dataset before building our machine learning model classifier. Here we cross-reference another section of the linked video on stratification and recommend you to watch to get a better understanding why we use stratified k-fold. Stratification of the new dataset is required to ensure a robust training of the model classifier and avoid overfitting. Now we will need some pre-processing steps due to different observations regarding distribution of features. The failure types rational speed and tool where have a non-normal distribution, therefore these features need transformation. We will need one hot encoder to encode variables. We need power transformer to make data more Gaussian-like, and finally need standard scaler to standardize features. All these can be realized with column transformer that enables you to apply data preparation transformations selectively, and finally it is required to create a pipeline that chains multiple steps together. For further model building, we need to get an understanding what multi-label classification and how multi-class classification can be defined. Multi-label and multi-class classification. For multi-label classification, the data must include more than one independent variable, also known as target class, and the cardinality of each class must be binary. There is more than one output prediction in this sort of categorization issue. The majority of classification machine learning algorithms are incapable of dealing with multi-label classification problems. To train multi-label classification data, a wrapper around machine learning techniques is required. This technique involves fitting one classifier to each target. This enables the categorization of numerous target variables. The goal of this class is to expand estimators such that they may estimate a set of target functions that have been trained on a single X predictor matrix to predict a set of answers. Multi-class classification can be categorized as a single output learning model when the output class is represented by the integer encoding. It can also be extended to a multi-output learning scenario if each output class is represented by the one hot vector. The purpose of multi-output classification is to train a classification model which output is a collection of labels, or vector. In comparison, the multi-label classification entails categorizing occurrences into numerous labels that share semantics, such as the difficulty of categorizing movies according to genre. A movie may be classified as either action or thriller, but it can also be classified as both, for example action-thriller. For instance, thriller and action movies share semantics. They both relate to the movie semantics, and are thus two different values of the same movie. It is also likely that a movie cannot be classified as any previously known genre, or that it is best classified as several different movie genres. Building a predictive model that simultaneously outputs a set of two or more labels that measure different concepts is thus the machine learning task of solving a multi-output problem. Essentially, two or more separate but related classification problems are solved concurrently within the same model. We will now test the dataset with different machine learning models, for example, random forest classifier, light gradient boosted machine, XGBoost, and Catboost. We will focus on tree-based and ensemble machine learning algorithms like light gradient boosting, random forest, and XGBoost classifier. It is possible to learn a multi-class classification problem using a binary classifier by using output code classifier class, as many machine learning models have been developed for binary classification. The output code classifier is used to fit each binary classifier to a multiple binary classifier. The class also provides the code size argument that specifies the size of the classes. Our first machine learning algorithm is random forest classifier. Random forest is an ensemble learning algorithm. Thus it is a combination of machine learning algorithms. The main differences between random forest and decision tree is that the training dataset is randomly sampled when creating trees and subsets of features are considered randomly when splitting decision tree nodes. The training data samples are made with replacements, also called bootstrapping. This means that some samples will be used several times in a single tree. The purpose is that by training each tree on different samples, each tree might have high variance regarding to a subset of the training data, but the entire forest will have lower variance without increasing the bias. And now, let us create a random forest classifier with our training data and make predictions with the created multi-output classifier and our test data. Finally, we calculate for each failure type the precision, recall and F1 score and visualize classification results on test data through a multi-output confusion matrix. Accuracy and Matthews correlation coefficient is in an acceptable shape. Our next machine learning model is Light Gradient Boosted Machine, which is a high-performing gradient boosting framework that uses tree-based algorithms used for ranking and to learn. It divides the tree vertically leaf-wise with the greatest fit since it is based on decision tree algorithms, unlike other boosting methods like XGBoost, which is splitting horizontally the tree depth-wise or level-wise. Growing on the same leaf in Light Gradient Boosted Machine, the leaf-wise approach may minimize loss than the level-wise technique, resulting in considerably improved accuracy, speed as well as less memory compared to any of the current boosting algorithms can seldom accomplish. Now, let us create a light gradient boosted machine classifier with our training data and make predictions with the created multi-output classifier. The multi-output confusion matrix reflects a few misclassifications, especially regarding failure type no failure, but overall a very good model fit is achieved as good as random forest classification. Accuracy and Matthews correlation coefficient is in an acceptable shape. Now, let us create a XGBoost with our training data and make predictions with the created multi-output classifier and our test data. The multi-output confusion matrix reflects some misclassifications, especially regarding failure type no failure, but generally an impressive good model fit is achieved slightly better than any other tree-based algorithm mentioned before. Finally, we calculate for each failure type the precision, recall and F1 score and visualize classification results on test data through a multi-output confusion matrix. Accuracy and Matthews correlation coefficient is above 98%, which is very good. A relative newcomer in the field of gradient boosting algorithms is Catboost. More information about this algorithm is linked in the video. We need first to download the necessary environment for fueling up Catboost. Now a Catboost classifier with our training data will be created and predictions with the multi-output classifier on our test data. The multi-output confusion matrix reflects some misclassifications, especially regarding failure type no failure, but generally an impressive good model fit is achieved slightly better than any other tree-based algorithm mentioned before. Finally, we calculate for each failure type the precision, recall and F1 score and visualize classification results on test data through a multi-output confusion matrix. Accuracy and Matthews correlation coefficient is in an acceptable shape. We have so far identified random forest classifier and Catboost classifier as the most robust tree-based classification models for multi-class classification with the method output code classifier. Now we would like to take the remaining two multi-class methods, namely one versus rest classifier and one versus one classifier, and apply them to random forest classifier as well as Catboost. We will start to apply one versus rest classifier with the Catboost algorithm. This multi-class method involves fitting one classifier to each class. It is also known as the one versus all strategy. For each classifier, the class is compared to all the other classes. We train and finally test our model. As also already seen before with previous classification algorithms, the multi-output confusion matrix reflects some misclassifications, especially regarding failure type no failure, but also here an impressive good model fit is achieved. We can calculate the balanced accuracy score, which is very important for evaluating classification models for highly imbalanced datasets. The accuracy score and Matthews correlation improved significantly compared to other algorithms. Next we take on the 1 versus 1 classifier with the Catboost algorithm. Fitting one classifier per class pair is the goal of this multi-class method. At prediction time, the class with the most votes is chosen. We train and finally test our model. As also already seen before with previous classification algorithms, the multi-output confusion matrix reflects some misclassifications, especially regarding failure type no failure, but also here it needs to be outlined that an impressive good model fit is achieved. We can calculate the balanced accuracy score, which is very important for evaluating classification models for highly imbalanced datasets. The accuracy score and Matthews correlation improved significantly compared to other algorithms. Finally, all the steps we have taken with Catboost algorithm will be also applied with random forest classification algorithm in terms of multi-class methods 1 versus rest classifier and 1 versus 1 classifier. We can recognize a relevant performance improvement of random forest algorithms by comparing key metrics like accuracy and Matthews correlation with previous multi-class random forest algorithms. Now let us build other models. We will change our view on this specific predictive maintenance problem with multiple failure types and handle each failure type category as binary classification problem. As earlier described briefly, we will now use the multi-output classifier method to train tree-based models. As a prerequisite, the failure types need to be binarized. For this we need to build a label binarizer by transforming and encoding each failure type to an extra column with 0 and 1s. Similar steps as previously shown are made to pre-process our data. We download the multi-output classifier for creating our classifier. First we start applying the light gradient boosting algorithm and train a model with our training data. Then for each failure type separately, accuracy, average accuracy and Matthews correlation will be created. After this, we create for each failure type confusion matrix. Finally, precision recall curve for each failure type is created. Next we apply random forest classifier algorithm and train a classification model with our training data. More on this algorithm is linked in the video. Then for each failure type separately, accuracy, average accuracy and Matthews correlation will be created. After this, we create for each failure type confusion matrix. And finally precision recall curve for each failure type is created. Our last algorithm for build a robust classification model is Catboost. We will apply this algorithm to our training data. More on this algorithm is linked in the video. Then for each failure type separately, accuracy, average accuracy and Matthews correlation will be created. After this, we create for each failure type confusion matrix. And finally precision recall curve for each failure type is created. At this stage we would like to evaluate our models in terms of costs related to incorrect classified validation data of our created models. A multi-class classification model will consequently also have a confusion matrix extending the already known 2 by 2 format. Most categorization metrics are binary by default. The classification problem's goal is to determine the class to which an observation belongs based on the collection of related characteristics. Typically, a collection of training datasets containing observations with known class membership is given, and classification is a subset of supervised learning in this context. A classification issue is classified as binary if the class label can only take two values, for example, A or B, multiclass if the class label can take several values, for example A, B, C, and multilabel if each observation is connected with many classes. In our predictive maintenance case, we'll have a 6 by 6 confusion matrix for 5 failure types and class no failure. All the diagonal values corresponding to each failure type are considered as true positive. The total number of true negatives for a failure type is the sum of the values of all the columns and rows excluding that failure type classes rows and columns. The total number of false positives for a class is the sum of the values of the corresponding rows excluding true positives. The total number of false negatives for a failure type is the sum of the values of the corresponding column excluding true positives. The previous trained multi-label classifiers with the function multi-output classifier have all high accuracy, recall and F1 score per failure type. Overall, random forest classifier and catboost perform slightly more robust and accurate comparing to light gradient boosted machine and XGBoost for multi-class and multi-label classification tasks. Anyhow, as with many other predictive maintenance tasks, cost-sensitive learning is main driver for classification model selection. The final assessment is therefore based on costs related to quantity of false positives and false negative classifications. As we have 5 different failure types, we need to consider that the overall maintenance costs differ among failure types. The cost impact related to false positives and false negatives per failure type differs, as well as false positives and false negatives related to class no failure. And here, we need to consider that false negatives related to no failure class, as additionally to maintenance costs, an undetected failure can result in severe machine failure and will cause costly production downtime. We will give this type of issue special attention later during the final model selection. Maintenance costs for false negatives of all failure type classes is sum of repair costs plus replacement of part costs due to misclassification of failure type. The overall costs of true failure type will be considered in the cost calculation. For example, in case of failure type which is a power failure, but was predicted as tool wear failure, maintenance costs will be calculated for power failure. Maintenance costs for false positives of all failure types takes replacement of part costs due to misclassification of failure type into account. The repair costs of the true failure type will be considered in the cost calculations, as costs for part replacements have been already calculated by false negatives. This approach is because misclassifications lead to wrongly assumed failure types and repair costs due to labor working hours are relevant. After making our cost calculations for the most robust and accurate classifiers random forest, light gradient boosted machine and catboost, we take the metrics from catboost as example to understand the cost calculations. Multiclass classifications as previously shown with the method output code classifier have a multi-class confusion matrix, which also described previously. The advantage of a multi-class confusion matrix comparing to a binary-based multi-label confusion matrix is that misclassifications to the remaining classes are shown in the matrix. Within a binary confusion matrix, misclassifications to other classes are not shown. For our cost calculations, the multi-class with output classifier is preferred as cost allocations for false negatives and false positives. We can see here that the multi-class classification with 1 versus 1 catboost model with total cost of false negatives and false positives is less costly, keeping in mind that only 20 false negatives with no failure have been classified. That would mean that in 20 cases there will be a machine failure and consequently production downtime without detecting a proper failure type. Unplanned production downtime due to undetected failures is critical for business and also reliability of machine learning-based predictive maintenance. In our calculations, the catboost algorithm was one of the cost-optimal multi-class classification model, and also random forest trained classifier was very cost-optimal. Severity of production downtime due to non-operational machines because of undetected failure types is multiple times higher and much more critical. So in conclusion, due to the low false negatives values for class, no failure, and transparency of multi-class classification confusion matrix, it is recommended to select catboost multi-class classification model as model of choice for our recipe. Thank you for your attention.